All right, what we're going to look at now is the different subsets of the real numbers. So in this case, the real numbers is going to be our universal set, and we're going to be looking at different subsets of the real numbers. Now, this is important because oftentimes you might be working in a scenario where you only want to consider whole number solutions, or you only want to consider rational solutions. So it's important that we know what those sets are so we know what types of solutions to present. So the first two are the natural numbers and the whole numbers. Now these sets are very similar, but there is one big difference. So the natural numbers are the counting numbers. I remember it as they're the ones that you naturally learn first. You start counting on your fingers, 1, 2, 3, and so on. So those are the counting numbers. Once you add 0, you are now talking about the whole numbers. And this is easy to get confused, but it's helpful to remember 0 has a hole in it. And so that's how you can remember which one is the whole numbers versus which one is the natural numbers. So the natural numbers and the whole numbers only differ by one element. Natural numbers is the smallest set of all of these, okay? Now, we do use symbols to represent these, which makes our life a little bit easier sometimes. And to name these specific real number sets, you're going to see that we use these double-barred letters, okay? So it's like a fancy way of printing. So the natural numbers is an N. So you see that it looks like an I-N. If you saw it printed, it would have like this. So it's got these double bars on them. The whole numbers is a W, so that's pretty easy. You can add these on the sides if that makes it easier for you. So far we've only looked at positive numbers. So now when we get to the integers is going to be all of the whole numbers plus their opposites. That's how we're going to get the negatives. Oops. Sorry, I erased that. So remember, in math, opposites only mean one thing. It means positive versus negative. Anytime you see that word opposite, we're talking about sign. So that set is going to look like this. It's going to go infinite on this side. Then we're going to hit the negatives, -2, -1, 0, +1, +2, ... That's how we can describe that using the roster method. The symbol for integers, natural numbers was N, whole numbers was W. So of course, integers is Z. Kind of weird, but that's what the integers are, is that Z with a double bar down the middle. Okay. You can peek ahead and see that the I is saved for something else. All right, we've got the positives, we've got 0, we've got negatives. Now we're starting to look between those numbers. So your rational numbers are going to contain fractions, decimals, and perfect roots. So here's what I mean. For example, the square root of 2 is a mess. That's not a rational number. You have to round that. So rational numbers are going to be your fractions and decimals that are nice numbers. They either are repeating decimals or terminating decimals. So I'm going to explain to you first in set builder notation what the rational numbers are. So I'm going to put this in the examples column. The formal definition, well, actually, I'll put it in the definition. The formal definition of rational numbers is this. All right, this is real mathy. So the rational numbers are going to be all of the numbers of the form A over B. Now, it doesn't mean they have to be written that way. It means we can put them in that form. All numbers of the form A over B, so that A and B are elements of the integers and B is not equal to 0. So 9 over 5, 1 over 4, 7 over 1. Any whole number can be written that way. Any negative number can be written that way. And then this also gets us to fractions and decimals. Now, this does not contain all the decimals, but it contains kind of the nice ones. So there's 3 things that you're looking for rational numbers. One is that you're looking for fractions. All fractions are rational numbers. They very clearly take the form A over B. Decimals, there's two categories. The first one is terminating decimals. This means they end. 5.7, done. 6.129, negative 0.00004. Those all terminate. They end. We don't have to round. We know exactly what they are. The third category is repeating decimals. 6.333333333, okay? And we've seen the kinds of fractions that those come from, like 1/3. 1/3 is 1/3, but when we try to convert that to a decimal, we get 0.3 repeating. So anytime we shorten that, we're having to round, but it does repeat 3333333 forever. So that would be a rational number. So here's some examples of rational numbers. Negative 2/3, 4.68, negative 1.333 ... Okay, so those are all examples of rational numbers. This is another weird one when it comes to the name. We don't use the letter R. R is reserved for real numbers, so rational numbers use the letter Q. And I believe it's Q for quotient. If you think it's A over B, Q is for quotient. I don't know what the Z comes from in integers, probably something in Greek or Latin. So, irrational numbers have a very complicated definition. That's a joke. Irrational just means not rational. The only kinds of numbers that are going to not be rational are going to be weird things like pi, e, and then non-perfect square roots or cube roots or any type of root, but not perfects. So, for example, some not rational numbers would be the square root of 7, pi, e. Let's say the cube root of 9. These are the ones, if you think of trying to have an argument with an irrational person, they're just kind of all over the place. Same thing here. An irrational number, if you put it in your calculator, it's going to fill up the screen. There's going to be no pattern. It's just going to be a mess. Those are irrational numbers, okay? And the symbol for irrational is the I, okay? The double-barred I. Real numbers is going to be everything combined. The symbol for real numbers is the double-barred R. You may have seen that before. I know I used it when I taught Algebra 1. And then essentially what that does is once you combine all of these sets together, you're going to end up having shaded in the entire number line. You've gotten all the fractions, all the decimals, all the weird numbers, and all the nice stuff, positives and negatives. So those are all of your different sets. So now we're going to use that information to kind of sort out some groups of numbers and see how they fall into these subsets. So let's move down. Before we do that, this is a really great visual that kind of helps you understand what we're looking at. Notice natural numbers is the smallest, whole numbers gets bigger, integers get bigger, rational numbers get bigger. Irrational numbers don't overlap with any of those, but all of them are in this rectangle for real numbers. This is a Venn diagram. It's kind of weird that it's rectangles instead of bubbles, but this is a Venn diagram, so you can see where they overlap. The natural numbers are all whole numbers, but not all of the whole numbers are natural numbers. All of the integers are rational numbers, but not all rational numbers are integers. So you can work from the inside out and still be included, but not from the outside in. Okay, so for number 9, what we want to do is take this set of numbers that we've got here and list all of the numbers in the set that come from each of the subsets, okay? So, natural numbers. Natural numbers must be just counting numbers. They must be positive, and they cannot include 0. And it may look at first like there are none, but if you think about the value of some of these, Clearly the fractions, the negatives, the decimals won't work. Square root of 5, that's not going to work. Pi, no. 7.3, no. But the square root of 81 is really 9 in disguise. And 9 is a counting number. So the square root of 81 is a natural number. Now let's look at the whole numbers. So whole numbers include 0, and we have 0 in the set, so 0's got to go in there. And then it's going to be all the other natural numbers, so square root of 81 is going to be in there as well. Integers is going to contain everything from whole numbers, but also the negatives. We're still not to decimals or fractions yet, so the only other number we can add to this list is -7. Notice our set is getting bigger every time because we're adding more sets to what we're looking at. So rational numbers now is where we add in our fractions, where we add in our decimals, and where we add in our perfect roots. So I say that because we have two roots here. Square root of 81, we've already said that's perfect, that's 9. But the square root of 5 is 2 point yada, 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 yada. So that's not a rational number. Pi is not a rational number, but all the other decimals and fractions are nice and good to go. So the rational numbers here are going to be -7 is rational, -3/4 is rational, -0. Oh, that one's not negative, sorry. It's just positive. 0.06 repeating. Square root of 5, not rational. Pi, not rational. 7.3 is rational. Square root of 81 is rational. And 0 is rational. Oops. I didn't put sets around these. You can put sets around the outside or not. It doesn't really matter in this case. Now again, the definition of irrational is everything that is not rational. And there were only two numbers that we did not include. We did not include the square root of 5, and we did not include pi. And then the real numbers is the entire set. -7, -3/4, 0.06 repeating, square root of 5, pi, 7.3, square root of 81, and 0. All right? Take a moment, put the video on pause, and try number 10 as a quick check to see if you've got it. And I will post the answers in 3 seconds. All right, here are your answers. Now, one thing to be very careful about, because it's easy to get used to something. The questions were not asked in the same order here. This happens on tests a lot. Because I use a test generator software, they get mixed up. So rule number 1 is read. Don't ever assume that it's the same. An example of this is on like true-false questions. Sometimes it might say A is true and B is false, or vice versa. So you must read everything, okay? So these are the answers. Now notice that on this example, our set had a name. And so when it comes to listing the real numbers, because it has that name, we can go ahead and use it to name it, because everything in set A is a real number. So that was nice that they saved you some time. If they didn't name it in this case, because the questions are asking you to list out the real numbers, I would list them all out rather than assign a name to the set. Just in this context, that's what I would do. So this always seems like a thing that should be easy. And I think that sometimes we look at it and say, oh yeah, I already learned that, so we feel like it is easy. This is just straight vocabulary, and yet these are the most missed questions on the first unit test. And it's simply because we don't invest the time to learn the vocabulary. So make a flashcard, make 6 flashcards, whatever you got to do to get those definitions down. These are definitions that you will be expected to know from here on out. So start studying.